A couple announcements first. Thank you to everyone who submitted assignment 5. I think everyone's pretty on time with that, so I really appreciate it. Assignment 6 will be dropped sometime soon. Still tweaking it a little bit, but yeah, it's not going to be as much work. But there's a bunch of fun things I put in there, so hope you enjoy it. Okay, yeah. So last lecture and assignment, we talked about modulation, demodulation, and things like that, but we never considered any non-idealities. And so this lecture, we're going to talk about that a little bit. And so one of the main things our modulation, demodulation schemes rely on is that we know the phase or the frequency of the received signal. So for example, when we try and demodulate, we send our information like this. This is the signal that's transmitted, and this is what we see in the received end, which is we have two information components, the in-phase component and the quadrature component. This is how we store information. And they're modulated by a sine and cosine. And this is going to be our received signal. And to demodulate it, what we do is we take this x of t and we multiply it by a cosine of t and take a low-pass filter to hopefully recover the in-phase component again, or do times 2. And then to recover the quadrature component, 2 times. We multiply by negative sign. And so the main assumption here is that.
Hello,
hey, David.
Wait, how come there's only 5 people here?
Welcome to RAC. The phase of our, this is times negative, of what we demodulate with needs to match the phase of our signal. But unfortunately, this is not the case. Over the air, we have frequency shifting and phase shifting. And it's actually important to understand how this occurs so we can understand how we can combat this, I guess. Or actually just more understand the nature of phase and frequency. So to give you an example, let's try and generalize a sinusoid. So we can say x of t is equal to, this is a general sinusoid, not necessarily a received signal, some amplitude times cosine of a phase. And so this is a very general way to express this. Your phase can be anything. So conventionally, we say our phase of t in a simple form is omega t plus some phase shift. Okay. And so the question you might ask is, if that's the phase, what does the derivative of a phase mean? Okay. Upon inspection, I mean, this is, if you look at this trivial example, the derivative of phase is just the frequency. And this intuitively makes sense because frequency is just how you go around your unit circle over a certain period of time. Right? The change in angle over your change in time is your frequency. Okay? So then, oftentimes, when our wave propagates through air, it may not change. This may not be a very accurate description of what our signal, what the phase of our signal can be expressed as. And so, when we try and demodulate with a sine and cosine at a certain frequency, this can be problematic because it can change in different ways. So it's important to know what the frequency of our signal is. Okay. As a little exercise, you could actually look at, say your signal is a cos of e to the negative t, right? And you could ask yourself, what's the frequency of this? Well, knowing that phase or frequency is just a derivative of phase, you know that your frequency, d theta dt, equals negative e to the negative t. So it's actually a really important idea to know that frequency is the derivative of phase, because knowing this, you can express frequency just by changing the phase of something. So I guess the question is, how is this manifested in real life? Okay. In real life, we live in what, 4 dimensions, right? Spatial and temporal. And so you can express a sinusoid as, say, a cosine of time frequency plus a spatial component. Okay. So if you were to, a real example of this would be, say you're standing at some point here in space, and here, we'll make this Prem standing right here. And for some reason, a fire truck is heading at him, or a police car, we'll say. It's that car. Okay. And the police car is emitting a siren, some sound. Okay. And Prem hears it. At one point, it's going to be, he's going to hear it at some pitch, right? And so, if you look at it, this equation, this is x1. Okay. Actually, this will be, say, one time instance. And then another time instance, the police car is closer now, very close to hitting Prem. That's okay, Prem's very strong. Okay. The frequency remains the same in both cases, but the temporal part, the spatial part changes. So the received phase, that Prem would receive, would change based on this. It'd be x1 minus, I guess the point is, you have phase changing. And so Prem is going to hear the frequency also changing, right? If you really wanted to express this, let me write this out here. It'd be like this. At position 1, x1, this would be your change in frequency. x1 minus x2 over the car's velocity.
Oh shit, sorry.
You're good. Tells you how much time has elapsed. And omega times delta t, I think. Wait, and then he receives phase 1, phase 2. And so the change in frequency would be essentially like this, right? Some time has elapsed, and he experiences two different kinds of phases, and so he experiences this change in frequency. His received frequency is different from what the transmitted frequency actually is because you have a spatial component of your phase that's moving, changing the effective frequency that you see. Okay. This would actually be the Doppler effect, by the way. You'll go more into this a little bit in assignment 6. I think a cooler example of this would be a wobbling planet or a wobbling star. If you have like a star, say it rotates around some tilt, okay? And it has a planet that's sufficiently big enough, when it rotates around the star is going to wobble like this way. And so what we observe actually is the light that we see from that star, it changes, it oscillates, because the distance that the star is to you is also changing, and therefore the received phase, the change in received phase results in a change in frequency, so you see different lights, even though it's still emitting the same kind of light. Okay. Kind of makes sense? Okay. Okay. Sorry about that. All right. Okay, so why does this matter? We need to match the frequency of the sinusoids we modulate our signal with, our received signal with, to recover our information. So just to reiterate, you have your received information, you have two components of it, and they equal, say, 2 times the low-pass filter of your received signal, x of t, cos. And yeah. So what actually happens is, well, if you look at specifically DPSK actually, if your phase doesn't match, your IRT equals your symbol sent times cos of how much you're off, and this equals this. So returning to our constellation diagrams, your sent signal will look like this, right? But if the phase that you receive it at is off, then you actually receive a constellation diagram more like this. Say your symbol's +1, then over time it's going to get rotated. And if it's -1, I wish I had a different color, we'll make it box axis. It's going to get rotated. And these go over here. And you can kind of see that, right? Because cos and sine, those are two components of a circle. So when you plot it against each other, it creates a circle. Okay? And this is actually very problematic because if you try and just interpret this diagram for just negative ones, for the -1 and 1, for your 0 and 1 bit, and you just make your decision boundary over here to decide, then half of your bits probably will be wrong, right? Mischaracterized. So that's quite problematic. So when we do try and recover a signal, we want our phase to accurately match the received signal. And so your first intuition, and it's a valid intuition, would be to use an FFT to find the received frequency. Okay. And the nice thing about FFT is that you can accurately find the frequency. Let's call it mega naught. And is there any other pro for this? Yeah, and like it's valid if the frequency at which you receive, the frequency of your received signal does not change a lot. So valid if receive frequency is constant, I guess. Or I think you can change that to constant. No, just constant, okay. But the cons of it is, because we're doing an FFT, you have no temporal information. It's a trade-off. And so, if your frequency does change, then you don't know it. It would be a more, on an FFT graph actually, it'd be, instead of a distinct spike, it'd be more of a gradual spike, like that. And so any one of these frequencies could be the valid frequency for a specific time instance, but you don't know. And so, not valid if frequency changes a lot. And I think the biggest point is that it has a time complexity of n log n. Okay. This is mainly the biggest point. In our actual implementation of the whole design process, we will have to use FFTs for filtering, but the less FFTs we do use, the better. We can process everything faster. Okay.
You guys want pizza?
Sure.
Yeah, kind of. Thanks.
Thank you.
See you with dressing.
We're not going to say no.
Gaps, right?
Yeah.
Cool.
Yes.
I've been to some of your.
Cool. Thank you.
If you were here, you get free pizza. Okay.
Wow, we are recording this. So, guys, for those of you who didn't show up,
Yeah, turn the camera around. Make sure
yeah,
everyone sees it.
show those huge boxes. Pizza, we've got cookies.
Yeah. And you just needed to show up and not be a lazy piece of shit or something.
David. Not on the recording.
Nobody heard anything. Okay, that's fine.
You have quite a bit of trimming to do. This recording.
I do. I don't think I will trim it, but okay. Okay. That should be the second idea. So okay, this clearly, it's actually very valid, especially for our case, but we can do better. That's the bottom line. So the second idea, which I think is a more powerful method, is the costless loop. So if we were to generalize our signal, we could say, like this actually. Okay. So costless loop begins with a guess, okay? unlike an FFT, we can't find the frequency just by looking at the raw data. So what you do with the costas loop is you guess some kind of frequency, okay? And the benefit of this in our communication system is that we already have a neighborhood of where our frequency can lie, which is our transmitted frequency, okay? And that may differ from our receive frequency, but it should be somewhere close. So if x of t equals a cosine of our receive frequency times time plus some phase, we can change this such that we'll call, we'll do a little mathematical manipulation. And I'm going to add and subtract the transmitted frequency times time into this equation. So it's still the same thing. And then what we're going to do is we're going to put this essentially in terms of our transmitted frequency. I should probably make this, actually S is fine. Sent frequency plus omega r minus omega s t plus. The point of this manipulation is that we can take this whole component, this offset, that we don't know, and just lump it in to some phase function, some arbitrary function. And this is a function we're going to try and keep track of. Okay? So the costas loop, what it does is we're going to try and create a phase offset, which we'll see later, to match this phase offset. Because we already know this, omega s times t. So we're going to try and match it. And I'll try and show you guys that in a second. Okay. So when we come to demodulation, we have our receive signal, or received information. And instead of, actually let's do this. So we know this, we can express our received information in terms of this, okay? So we'll put cos of omega s times t plus some arbitrary phase. And then for the in-phase component, multiply it by a cosine, omega s times t, and then we'll multiply or have some additional phase component. And this is something we'll control. We control this. Okay. Do the same thing over here. Try and write this a little faster. Okay. And what this evaluates to is this. Cos r. So it'd actually be, sorry. Should be IS and IS. Cos of omega, no, sorry. D of t minus theta of t. It evaluates to the differences of our phases now. Okay, So these two equations should look kind of similar to what we have over here, in that, sure, our phi of t is arbitrary, and theta of t, but it instantly creates a circle like this. But if we can find a theta of t such that these two cancel out, we recover our information. Okay? So you can look at it as like trying to maximize IRT in a sense, or maximize, or minimize, I guess. This would be your optimization problem. Phi of t minus theta of t. Okay? Or the opposite. And so the solution to this is obvious, except we don't know what phi of t is. So we need to create like a smarter way to track it essentially. And that's what the costless loop essentially tries to do. So let's see, how do I want to do this? Okay. The first thing we should do actually is, if we're trying to minimize something, we can put it in terms of a cost function, okay? And so this kind of problem is equivalent to maximizing your in-phase almost, right? Because when these two cancel, then you have your symbol recovered, okay? Except the problem with this is that IS of t is in the set of -1, 1. Okay? So we're actually going to try and maximize the square of it. Okay, so you try and maximize it turns to IS of t squared times cos squared of phi t minus theta t, which is just equal to the cosine squared. Because this goes to 1. A couple of things about this is that we receive a maximum, maximizes at every 0 plus pi n, right? There's infinitely many solutions, and we just need to try and track it. Okay, so to track this, we're going to use a combination of gradient descent and PID. But before we get into that, let's do a little refresher on what those two things are. Okay, so let's say in the problem over there we have cos squared of theta, or phi of t, capital Phi minus theta of t, which is equivalent to minimizing phi of t minus theta of t, absolute value. Okay? And so we don't know the shape of phi of t, but it could create a contour like this, right? And so the idea of gradient descent is that, okay, we have our guess theta t, and we're going to try and approach this iteratively, okay? So we find our phase difference, or we find, I guess, the derivative. So say we're at this point on our curve. This is the difference. We see what's the slope at this point. And using that slope, we try and update our theta, our phase offset, proportional to the derivative of it, okay? So we'll call it J of theta. J of theta is actually going to be this. Oops. Squared, I think. Or it's going to be the, yeah, go squared of. I'll go into later, actually. Okay. The point of gradient descent is you find the slope, and you try and approach this minimum by, tracing along the contour. Even though this is not exactly convex, hopefully it will find us to some minimum. We do have the advantage that we have infinitely many solutions, and so we can try and just get close to one of them. Yeah. And also because there is infinitely many solutions, you could also express this as this. Equals theta old plus. And this is, I think, the implementation we'll stick with. Okay. Yeah, that's kind of an overview of gradient descent. Let's talk about PID before we actually go into how we're going to do this. PID, so this is a quick refresher. It's a control method to find an optimal value. And so an example would be you have a car, your ECE3 car, and you are currently facing some angle, and you want to turn to a target angle. Right? So PID is use a proportional integral and derivative controls. Proportional would be like, okay, here's my current angle, and I need to turn these wheels such that I turn to that angle. So we'll say we'll set the motor out speed. We'll call it ms is equal to some proportion times how much we're off. And this works because when our target angle equals our current angle, we're not moving anymore. But it turns out theoretically, you won't actually ever reach your target angle with just a proportional controller. The math behind that, I don't think is necessary to go into. But oftentimes I use an integral controller. And the idea of an integral controller is, let's say you have your target angle, and this is your error, or target angle, we'll call it error. And this is time. With a proportional controller, you will approach it like this. With an integral controller, which is you just take the sum of your error over time, times some constant, you will eventually converge onto this. Because you're taking the average error you're away up from it, and you're using that to align to the target, right? Because eventually, your it'll eventually converge. Okay, that's a bad explanation, but the main idea I want you guys to take away from this is that we have two ways, two control methods to converge to a solution. You have scaling your error function, and then the integral of it too, just a summation, and some output. Okay. We're going to try and mix this into gradient descent to hopefully form a valid controls method. Okay. So, the thing is, so far, with the math we've drawn out on this one over here, is we have an error function right here, but we have no way of measuring it. So, how can we measure this? Well, using the lens of gradient descent, we try and update our angle with the derivative, okay? Try and approach it using the derivative. So let's try and take the derivative of our cost function. So at a high level, our cost function will be this. I'll call it J. That's the notation I used. I don't like the notation I used. It's okay. Let's call it JC. No parameters. Equals the low pass filter, or we can do 2 times it, of x of t times cos of omega t plus theta of t. And we're going to square the whole thing. Let's remove 2 for now. Okay? And so this is equivalent to this, if you recall. But we got to take the derivative to see how this turns out, because this is information we actually have. This is a function we actually do, and we can do this modulation over here. So let's just see how it behaves. Let's take the derivative with respect to okay, we're going to see how does this change when we vary this. Okay. So right off the bat, you have a square, so it becomes a bunch of chain rule. 2 times low pass filter, keep the inside, x of t, cos omega t, plus theta of t. And then times chain rule, which would be low pass filter is linear. We're going to assume it's linear, so we can shift the derivative inside. And so it's just d theta of, or low pass filter of d theta of x of t cos of omega t plus theta of t and then let's keep this down. This would just be a low pass filter of x of t times negative sine of omega t plus theta. Okay? So, quick observation. Okay. Look right here. This is just our in-phase component. This is us just demodulating normally. And this is the quadrature component. how we demodulate that. And if you actually compute the low pass filter and multiply it out together, knowing x of t equals your in phase times the cos of omega t plus some arbitrary phase. This equals actually, I'm going to sketch this out, Actually, it'll do this actually. I of t squared this component, as you know, is 1/2 I of t times cos of phi minus theta. And then this component is 1/2 I of t times negative sine of phi minus theta of t. These parts squared, right? I of t times I of t, that goes away. Cos times sine gives you sine of 2. It's a double angle identity. P of t. And then 1/4. And you can put a negative on there. Or shift it inside, doesn't matter. And oftentimes, you can just take the first order Taylor series expansion, and what you get is this. Phi of t minus theta of t. I think that's right. Okay. That's 1/2. Okay. You're able to find the phase difference by taking the derivative. Okay. Knowing that this is just demodulating over here, and then multiplying the two signals together, we know we can physically realize this. We can physically realize finding some kind of error function, our phase offset. And that's kind of what the Costas loop is. We're going to take this phase offset, and we're going to use PID and gradient descent combined to hopefully minimize this. So if you put this back into gradient descent, actually, what you get is, okay, iteration by iteration, we're going to say our new angle every time we try and go around, and we try our prediction for the next angle, right? That's what this is trying to say, equals some constant times our error function. Okay? And this is synonymous to PID right here. This is your proportional component. Kp times an error. And what people often do in industry is they say, oh, okay, if this is our proportional control, let's add an integral component. And it looks something like this. I'll do I think I'm mixing discrete and continuous too much for the integral. Okay. You can turn integral into a summation. You go to discrete. So, And this is actually a very effective model for tracking your phase. And the introduction of it is kind of interesting, knowing that you're mixing controls with gradient descent. But there are actually many similar optimization models to this, okay? Gradient descent, if you've ever taken a machine learning class, is one way you can approach a solution iteratively. But you can also use like momentum. And this is actually quite similar to momentum. I think the formula for momentum is theta nu, right up this way here, equals theta old plus the summation of our, I think it's some epsilon times, we'll call it your error function, plus summation of, call it alpha, the error function, plus, of course, okay, something like this, okay, where you have some integral component, a proportional component, and you use that to find your old and new phase, okay? This is, I think, a little bit more accelerated. Keep in mind, you can actually use both. Either should work. This is the standard way of finding a minimum in industry. I actually haven't tested this to know, but I'm sure you can make it work using this one too. So that's kind of the causes loop. Before I finish this, I'm going to draw the block diagram to show you how it's actually implemented in hardware or software. So to implement this in hardware, what you have is your input signal. And remember, we're going to try and find the in phase and quadrature components. That naturally comes out as our error function, right? So we're finding our error function first. And what you do is you create two branches. And the first thing that happens is it's mixed with a sine and a cosine. And then that goes, it's low pass filtered. And then we go and we multiply them together. Keep in mind, here is your in phase. Here's your quadrature. And knowing this, you can pass it through a loop filter. And then it goes here, where you just say this is your output data, and you pass data into these modules, the sine and cosine. And this is a cost of loop. And it actually produces some very good results based off scope data that we collected last year from RAP. we were able to demodulate a signal just by guessing the frequency. We were able to demodulate a signal that was 100 kilohertz off. So basically 10% off of the frequency we sent, and was still able to get it. So it's a very flexible model, I guess you could say. Yeah. So that's the closed loop. We'll be implementing this. Any questions?
Should we take a break or?
That was it.
That's it?
Yeah. How long did I take?